All right. So we are trying to understand now what is the best design, mainly concerning my AS1000, right? Because the rest of the ASs are basically eBGPs, right? But inside my AS1000 we'll have a lot of things happening now. We'll have eBGP, you'll have iBGP, and you also have some kind of IGP. IGP is maybe like OSPF or ISS, eIGRP, or whatever it is, right? So all of these concepts would come together, right? So let's start by maybe let me put up a very simple example to explain this, right? So let's say I have this is my AS1000, right? This is my AS1000, which is cool. Let's say I have a bunch of routers, right? 1, 2, 3, 4, 5, 6, maybe 7 different routers, right? Now these are the provider edge, right? And when you design a huge network, what they do is they create one separate provider edge for different ASs, right? Let's say you have a different AS here, right? And they create kind of like uh, different provider edges for each of these different ASs. So now let's say R1 will be talking to this guy, R2 here, R3 here, 4, 5, 6, and 7. This is how it talks, right? And then obviously these guys will be further connected to the internet, because at the end of the day, a network of ASs, it's nothing but internet, right? So this is how it looks. Now you know that in BGP, to form neighborship, right, there are two things. You don't have multicast, it is unicast based. BGP is unicast based, right? Which means that when you form the neighborship between two routers, right, it is going to be unicast. The hello packets and all of that is going to be unicast, right? And that is governed by the neighbor command, right? So between R1 and R2, if you want to form a neighborship, right, it's going to be like this. You need to define a neighbor relationship. Between R1 and R3, you need to do it again. Same thing for R1 and R4, 5, 6, and 7. Now same thing would repeat even for R2, right? Now R2 will have to do it with R2, R3, and so on. So if you look at this, at the end of the day, it is going to be like a very big of a mesh network over here, right? It will be like this, a mesh kind of neighborship. And this is not obviously very it's obviously not very optimal, right? You wouldn't imagine you have a AS with probably 500 routers, right? You can imagine the number of neighbor relationships it has to form, right? Obviously not a very optimal way to fix this or work this problem out. So how would you do it, right? How would we do it? So in that case, let's say, let me just get this off. Okay, let me actually get the whole thing off and probably do this again. So the optimal way to do this would be, let's say this is my AS1000, right? And I have my routers like earlier, 1, 2, 3, 4, 5, 6, 7, right? You have these routers more, you might have more as well, and so on. But normally in a network, you have what you call as the core switches, right? So you will have a bunch of core switches. Let's say we have a couple of core switches here. Maybe this could be very highly powerful, say maybe the nexus switches, right? And they also give these, all these routers will be connected to these core switches, and they also, because you want redundancy, they'll be connected to both of them, right? Something of this sort, right? R1 is connected to both the switches, R2 is connected to both the switches, and so on, right? This is kind of a topology which you generally see, right, in a network, right? And the core switches along with these routers, they will be running a IGP as well, right? So you'll have an IGP, say maybe OSPF or something, right? They will be running underlying, they will be running, right? So along these red lines which are here, right, you will have like a IGP running, right? So this will be the current situation in any network, any service provider network. If you see, this is how it would look. So these are your P's, right, over here. The 1, 2, 3, all of these are your P's, and you have your core switches here. Okay. Now the interesting question would be, in such a scenario, when you have to form the neighborship, let's say you have to form the neighborship between R1 and R2, right? You still have the you still obviously have to form the neighborship, right? So for forming the neighborship, you need to mention the IP address, right? Neighbor, and then you need to mention the IP address. So on R1 you mention the IP address of R2, and on R2 you mention the IP address of R1. Now if you had like a one-to-one kind of neighborship, right, in that case, if there was only one link between R1 and R2, you would have easily used the IP address of that particular link. But here you see, right, R1 is connected to the switch via two links, and R2 is connected as well to the switch via two links, right? So which of the IP address would you use, right? So that's why in a very good design, what they do is they use the loopback address, right? You will have a loopback address over here, let's say loopback 0, and here also loopback 0. So when you form the neighborship between R1 and R2, you will use the loopback addresses, because what happens is, even if your physical interface goes down, let's say one of the interface goes down, right, let's say for R1 this particular interface went down, right, you will still have a path to reach R2 via the other link, right, because other link is connected to the other switch, and R2 is connected to that switch, so you'll have that connectivity, right? So this kind of gives you the flexibility of redundancy as well. So there is redundancy, and that is why we mainly use for the neighbor commands, we normally use the loopback interfaces, because they are virtual, right? They are not physical interfaces, they will not go down. But if the physical interfaces goes down, you will always have a backup route to the loopback interface, because you have like a, in the backbone or the underlying network, you have a IGP running, like OSPF or ISS or whatever it is, and you'll be able to reach to that guy, right? But we still have the problem of the full mesh network, right? We still have the problem, because currently what's happening, every single guy will be connected to both the switches like this, right? And you will still have to form neighborship, right? R1 will have to form between R2, and R1 will have to form for R3, R4, and all of that. What we just solved using this mechanism is that we kind of added redundancy. And how did we do that? By adding by creating neighborship with the loopback addresses and not the physical IP addresses or the interface IP addresses. So now we still know that we have to still fix the full mesh neighborships, right? Because full mesh neighborships are not obviously optimal, right? So let's say I go and create my AS1000 here with, say, just three routers, right? Let's say R1, R2, and R3 here, and R3, right? Now why doesn't why can't we just do this, right? In my regular IGPs like OSPF, RIP, eIGRP, we used to do this, right? We used to just create neighborship between R1 and R2, and R2 and R3, right? So that way, the routes which are learned from R1 inside R2, right, R2 will then send them to R3. But this doesn't work. Why this doesn't work? Because in iBGP, to be specific, we have we can't set up neighborships of this sort in iBGP, because we have split horizon rule. And as per split horizon rule, what it tells you that is that R2 can't forward the routes from one iBGP neighbor to another iBGP neighbor, which means, right, the routes which are learned here like this, iBGP will not be able to send it along R3, right? That is done just to prevent all routing loops, because iBGP doesn't change the AS path number, right? But you need to understand that this is not possible because of the split horizon. Now how do you fix this? Because if you fix this, then we can obviously fix the other problem, which is preventing full mesh neighborships, right? You'll be reducing the neighborships in your AS, specifically for iBGP. So how do you fix this, or how do you get around the split horizon, is using your route reflector, right? So in route reflector, we basically create one central router as your route reflector. Okay, so let's say, right, so we create one single router as my route reflector. So it will look like this. So I still have my this guy, my R2 is here, right, my R1 and R3. So R2, let's say R2, we create R2 as my route reflector. This is how it works. So this guy is my route reflector, right, and it is connected to R1 and R2, right? Probably even this is connected, not an issue. Now route reflector is allowed to receive a route from iBGP neighbor and forward it to iBGP neighbor, right, provided both are its clients. So you don't have to even configure anything on the clients. You just need to do the configuration only on the route reflector, and you need to tell the route reflector that R1 and R3 are clients, right? And when you make this a route reflector, the routes which are learned in this direction, they are reflected as is to R3, right? That's why you call it as a route reflector. It just reflects, it doesn't change anything, right? So we now solve the problem of full mesh as well, right? So route reflector helped us get over the split horizon, and because we were able to do that, we kind of no longer have to create lot of neighborships in the network. So here in this very topology, you just need to create neighborship for R1 to R2 and R2 to R3, as simple as this, right? It's just two neighborships. Now imagine if you have a lot of routers right here along with R1 and R3, you had a lot of routers, right? So you no longer will have to create you know neighborship or a full mesh neighborship. You just have to create neighborship only with the route reflector, and the route reflector will then kind of send it downwards, downstream to the other. The routes basically will be sent to the other guy. Okay, but is there a bottleneck, right? In this particular example, will there be a bottleneck? Because will all the traffic have to go to R2 and then reach the other routers? Is that the case? Actually, no. So route reflector reflects the routes without any modification to the attributes, right? So this is very, very interesting. Let me draw this again. So how this works is, so you have here, this is my route reflector now, right, or R2, and let's say this is my R1 and R3, right? So the route reflector, like I said, it reflects the routes without any modification, right? So let's say um, route reflector received a route from R1 via the iBGP, right? It came here. The next hop was equal to R1, right? Let's assume the next hop was R1 here, right? For the route which it learned in this direction, the route reflector has a next hop of R1, and this route will be now sent down here with the same next hop. It won't change anything. So the next hop here also will be R1, right? Now what will R3 do? Right, for R3 it will look into its routing table, and like I said, there will be generally an IGP running here, right? OSPF or something will be running, right? So it will look into its routing table, probably pick up a route, and to reach the next stop, which is R1, right, it will look at the best path, and in this current topology, clearly the best path is going to be this, right? So if I'll probably use a different color here. So the best path is going to be this one to reach the route. So what did we establish here, right? Because your route reflector is not changing the routes, not changing anything in the route, even the attributes, right? It is keeping everything same. The next stop is also same. As a result of that, only the routing updates are going to the route reflector. Only the iBGP routing, updates are going to the route reflector, whereas the actual data transfer, will can still happen based on the best route given by my IGP, right? So RR is not creating any bottleneck, because whatever is going towards it is only the control traffic or the iBGP routing traffic, the routing updates and so on, right? Whereas the data will still take the underlying IGP which is running, right? So BGP is a very interesting protocol this way, because it helps you to differentiate the control traffic and the data traffic. Here clearly you can see the control traffic is this one, right? This is basically my control traffic, and it is going to the route reflector and coming down, whereas my data traffic, right, which is on my R3, it is taking the best route, which is towards R1, is obviously this direct path. It is not taking this above path, it is directly taking this path, right? So this is actually how everything comes into everything is put in place, right? You have the iBGP running here, you have the IGP running here, right? And how all this interrelates is really beautiful, and that's how BGP solves a lot of problems, right? So if I have to draw a final diagram of how a BGP design looks like, this is how it would look. Let me delete this, right? This is how it would look. So let me pick up a color. So this is your, say, your AS, right, your company, right? So this is your organization, right? And you will have lot of you'll have like lot of ASs over here, right? You'll have like A, probably another AS called B, C, and so on, right? You'll have many of these ASs. You'll have routers here, the provider edge routers. Generally, if it's a very big network, you'll have like R1, R2, like different routers for different, different ASs this way. Okay. Then now let me use a different color for the data traffic. How does the data traffic work? Because you have the switches here, core switches, right? Generally a core 1 and core 2, and every of these guys is connected to both of them to give you the redundancy, right, which we talked earlier, right, this way. Great. And you will have a like a OSPF or something running here, like a IGP will be running, not necessarily OSPF. It could be EHRP, RIP, or anything of that sort, but you'll have like a IGP running here between R1, R2, R3 and your core switches, C1 and C2. So R1 will be able to reach R2 via this IGP. Okay. Now what you do is, now you need to also run iBGP, right? You want to run iBGP, because why are we even running iBGP? Because you want to retain all the attributes. We learned that earlier. We want to retain all the attributes of all the routes which are learned, like this in this direction, right? So you want to retain that. So what we do is, we have to, let's say, use a different color here. Let's go and create two separate routers, right, which is going to be your route reflectors, right? I'm creating two because, for redundancy again, right? And these route reflectors are going to be connected to obviously my every single router here. Okay, this way. And what will these route reflectors do? They just carry the iBGP control traffic, no data traffic at all, right? So R1, basically this is how it works. Finally, this is how it works. So R1 receives a route from A, right? Let's use a different color to show this. Let's use orange or maybe pink. Yeah. So R1 receives a route from A in this direction. Here it comes in. Yeah. And R1 will send this particular route to the route reflector, because it has formed a iBGP neighborship here, right? So R1 will send it to R with the next stop of say R1, right? So this route came in here, it came here, right? This route came here with the next stop of R1, right? With the next stop of R1, right? Now because route reflector's job is to reflect the route, the same route will be reflected to R2 and R3 and R4 and so on, right? And the next stop will be same. It will be, when it is reflecting here also, the next stop is going to be R1, here also next stop will be R1, everywhere it is going to be the same thing, right? Now let's say R2 has to send some data to R1, or it has to send some data to this particular network, right, this AS. So it will look up this particular route and it will find that the next stop is R1, because it received it as R1. It will look its internal routing table, and it will route this packet, or it will send this packet using this backbone OSPF or IGP, whatever we have, right? So it will send this packet along this. It doesn't have to send it to route reflector. Instead, it will send it using this amazing IGP which we are running underlying, right? So this is how the whole concept is put in place, right? We have the iBGP running, to mainly for the control traffic, whereas the underlying IGP, which is your OSPF, ISS, whatever it is, that will contribute and that will carry my data traffic, right? The other interesting thing which I want to call out here is that by segregating the control traffic and the by doing this, like we have these both here for the control traffic, whereas you have these both, or the mainly the core switches here for the data traffic. What are we doing is, we can plan our infrastructure better way, right? So on these switches you probably would need a lot of speed, right, because you have like all the routing happening and all of that, so you need a lot of speed here. You'll have to do a lot of switching down here, so you can probably use like heavy nexus switches, right? But at the same time, my route reflectors here, you will need to have a lot of memory, because they have to like store all the BGP routes coming from everywhere, coming from all the ASs, right? They'll have to store them. So you can like use route reflectors. Basically you can use routers with very, very high memory, right? Cool. So let's go back and probably try to put some of these configurations on my topology and try to understand if whatever we discussed now is actually valid. So now we will start by configuring everything which we have studied till now, right? So we'll start with configuring the iBGP in this segment, right? R1, R2, right? But before that, what is the prerequisite? Like I told you, prerequisite is that we need to have a IGP running, which is say OSPF, eIGP or something, and you need to have each of these loopback addresses of R1, R2 and R3. We need to have at least one loopback address of these routers inside that IGP. That's like the prerequisite, right? You will understand why that is a prerequisite when we go and configure. So what we'll do is first we'll create this IGP. Let's use something very basic, which is my eIGRP. Let's create router eIGRP 100, right? And let me go and advertise my networks, right? So it's going to be 10 dot okay, let me advertise these first. 192.1.12 network, 12.0. It's the network between R1 and R2, and the other one is 13, which is between R1 and R3, right? Now if you look here, to show IP interface brief, I also have a new loopback, which is loopback 10, right? And this is the loopback which we'll use for creating our BGP neighborships, right? So we have to advertise this as well. So we'll go and advertise 10.1.0 0.255, right? There you go. So on R1 it is done. Let's do the same thing here as well. 100 network, here it is 10.2.2.2, and then other two guys are 192.1.12.0, and the other one will be between 2 and 3, it is 23.0. Okay, the last one, and the last one is on R3. Okay, I've already done it here, so it's just router eIGRP, and I've put in this thing. Let me also do no auto summary here, and do no auto summary here as well, right? So there you go. So we clear all of this, and I can show you what we have done, right? So I have basically set up I've basically set up IGP in this domain, which means let's say on R1 I can do show IP route eIGRP, and you can see I have connectivity to 10.2, and the 10.3 also should be visible. Maybe, let's see, have I not done that? Do show run section router 10.3 dot looks good. Yeah, I don't have the network, that's why. So I'll create a loopback 10, and the address will be IP address 10.3.3.3 and 255.0. Okay, now if you look here, right, you can see I have eIGRP routes to both my loopback addresses, which is 10.2 and 10.3, right? So we have the prerequisites in place. Now we are good to configure iBGP between these routers in this domain. So let's do it between R1 and R2 to start with, right? So what do we do? Let's look into what we have. Show run section router BGP. This is what we have. What do we do now? Router BGP 1000. Two commands are important here. One is a neighbor command, 10 dot, you're forming it with R2, right? Let's do 10 dot, and then remote AS is 1000, and the other one is the update source command, right? I'll tell you why it is needed. The update source will be loopback 10. Okay, now why did we do this? Why did we do update source, right? I'll tell you this once I do the configuration on R2, right? So let's go to router BGP 1000 here. Is already run, sorry, my bad, I put in 100. Let's do no here, and let's do 1000, right? So on R2 we do same two commands, which is 10.1.1.1, which is the loopback of my R1. It is in line with what we discussed earlier. We are trying to form neighborships with loopbacks, and not with physical interfaces, because this helps you create those redundancy. And the other one is we just need to put in the update source as well. Update source, loopback 10. Just hold on for a minute. I'll do all this, do the configuration on my 3 routers, and I'll explain you why I did the update source. 1000 and neighbor here. We are doing, should we, or let's not do this on R3. Let's just keep it on R1 and R2 for now, right? Now on R1 and R2, if you see here on R1, I'm telling my router that the neighbor is 10.2.2.2. On R2, I'm telling my neighbor is 10.1.1.1, right? So the routing updates, let's say a routing update going from R1 to R2 will have a source address of what and the destination of address of what. The destination address would be this one, 10.2.2, because we are explicitly telling that is your neighbor. But what will be the source address? The source address would be the outgoing interface here. It will be 192.1.12.1. So when that packet reaches on the other side, right, the other side, it will only form neighborship if the source address was 10.1.1, right? Because you're explicitly telling here that form a neighborship only if the source address is 10.1.1, right? But we did not receive that. We received the source address of the basically the outgoing interface here. So that's why we manually override and we explicitly tell that when the packet goes out, don't use the outgoing address as the source address, rather use 10.1.1, which is basically the loopback 10, right? That's why you do it on that. Okay, great. Now next, let's go to R2 and look into some stuff. Let's clear this. So on let's go back on R2. Okay, so on R2, let's look into what? Let's look into my table, BGP table. Show IP BGP. What do you see here? Let's concentrate on this 4 route, right? This is my 4 route. Now the 4 route, if you see, doesn't have this greater than mark. You can see all the other routes have greater than mark here, right? This one has, 5 has, but 4 doesn't have it, right? Why? Because you see the next stop for this route is 192.114.4, and from R2 you see that route is not reachable, right? It is here, 192.1.14.4 is this one, right? And on R2 I don't have that in my routing table, right? Show IP route, right? I don't have or I could, yeah, so I don't have this route, right? 192.1. You don't have the 14 route here, and that's why whenever the next stop is not reachable or not in my routing table, that's when the greater than mark doesn't appear in the BGP table. How do you fix this? One way to fix this is obviously just take this route and advertise it inside my eIGRP, right? This route, the 192.1, and then it would appear. I could show you that, but that's not how we do it, but I'll show you that, right? So if I go to my router eIGRP, did I use 100 or 1000? I forgot, probably 100, right? So I go inside that, and network, I do 192.1.14.0. If I do this, right, if I do this, what would have happened? Now if I refresh this, sorry, let's clear this, right? Now you can see the question mark has come because R2 is able to reach this particular route or this IP address, because now we have advertised this into eIGRP. But that's not how we do normally in a service provider network, because this link is not ours, right? This is my AS, this is my company, and I generally, because of contract restrictions and all of that, they will tell me not to redistribute or sorry, not to even advertise this network inside my AS. So I can't do this method, which means I will go here and do a no. I just wanted to show you that technically it is possible, that's it. So I did a no here. So as soon as it did that, this should go off. See, it will take some time, couple of minutes, but you see it has gone, the question mark has gone. So how do you fix this? So to fix this, right, so why did this even happen? Because the next stop was being picked up, this one was being picked up as next stop, and as this route got inside my AS, right, the same next stop was propagated, right, so the next stop was R4. But to fix this problem, what I can do is I can do next stop self on my R1, right, so once the next stop becomes next stop self, right, R2 will be able to reach this guy. So I'll show you that. So on R1 I'll go and I'll tell, right, so what I'll do is I'll basically say next stop self, right, so this is my R1, right, I have to go inside my router BGP for doing that. Router BGP 1000, sorry, 100, the neighbor command, sorry, not 100, it should be 1000, right, 1000, and now I will tell neighbor command 10.2.2.2. we had done this earlier, we're just putting in next stop command along with this, next stop self, right. So I told BGP that for this neighborship, whenever I form neighborship, when the routes are being exchanged, please exchange the routes with by changing the next stop, because in BGP by default it doesn't change, it just sends the R4 itself as the next stop, but here I manually override it. That's why now if I refresh this, still you see it is not at refresh, it's still showing R4 as my next stop. Let's see, let's take a minute, it will take some time for the changes to be seen. Yes, now you can see the changes have occurred. For the 4 network, it now takes R1 as my next stop, and you can see the greater than mark has also come because it is reachable, right. My routing table will basically have it, and that's why you can you'll be, and that's why this route will now go to my routing table. I can show you that. Show IP route, yeah, so you see the 4 network is here and it is present, right. Does even R5 have received it? Yes, the R5 also should have received it, because you have eBGP over here between R2 and R5. So I can do show IP route, you can see the 4 network is here and it has received it. Okay, now the question, can I ping my 4 network from R5, right, from R5 can I ping this 4 guy? Let's try that. Ping 4.4.4 source 5.5.5. you can see the ping is not working. Just because we have a route here doesn't mean that the ping will work, right? Why the ping is not working? Because of the same problem, right? So what happened for R4 on R2, the same issue will happen for the PHY network from R5 on R1, right? So if you see on R1, show IP BGP, you can see here the PHY network, right? The next hop is 25.5, which is not reachable. So to fix this, I'll have to go on R2 and make it as next hop, right? So let's do that. Configure router BGP 1000 neighbor 10.1.1 next stop self. I do this, what will happen now? Still it is having the old one. Let's wait for a few seconds. BGP is a bit slow, it takes a bit of time sometimes. Yeah, has it happened? Yeah, now it has happened, right? You can see for on R1 the PHY network, the next stop is 10.2.2.2, right, which is reachable. So now you have routes for both the directions, right? Earlier we had only one direction, but we kind of, even for the reverse path, we kind of fixed the issue, which means now we should be able to do this ping. There you go, see, it's working, right? That was good. Now let's do the same activity on the other side of the network, which is here, R5, R2 and R3, this side, right? Basically we want to do it on the right side of it. So we go to R2 and we do neighbor 10.3.3.3. remote is what? Remote AS is 1000, right? We did it for R2, and let's also do the rest of the two commands which is needed. One is your update source is loopback 10. We know why we are doing this, and we also need to do the next stop self, which we know why we are doing this as well, right? Great. So that was on R2. We'll do the same thing on R3 as well. BGP 1000 and neighbor 10.2. Remote AS would be 1000 and update source would be what? Loopback 10, and the next stop self is also needed. Good. So now on R3, if I look at now on R3, if I do show IP BGP, you'll find the 5 network which is coming from the other side, right? You have this 5 network is also visible on R3, and the next stop will be R2, which is 10.2. Right? So we have done iBGP on this side and this side. Now if you observe carefully here, let's look at the 4 network, right? The 4 network, you see it is receiving this 4 network from R6 and R7, right? R3 is receiving the 4 network which is here from R6 and R7, from these both guys, but it is not receiving from R1, right? It is ideally supposed to receive from R1 because that is how we designed it, right? We put in iBGP here so that it receives this route from R1, but it is not. Why? Right? Because what has happened right now is that route, the 4 route which was learned on R1 went to R2, but R2 was not able to send it here because of the split horizon concept which we learned earlier, the iBGP split horizon. Because of that, this route is not coming down here. So how to fix this? We basically make R2 as my route reflector. By doing so, we will kind of get away with split horizon, at the same time reduce the neighbor relationships, kind of reduce it from full mesh to quite significant less number, right? So how do you configure route reflector? You just go to R2, clear this a bit, and to configure route reflector, we basically go inside, say, router BGP 1000 neighbor. Which are the 2 neighbors we want the route reflector to be part of? This is going to be my route reflector client, right? You just make R1 as your client, you make your R3 as your client. You make R3 as my client. There you go. We made R3 as my client as well. Right? So do you think this would have helped? Let's go to R3 now and let's see what has happened. Now you can see for R4, for the 4 network, it is receiving it from R1, right? So what we did was, by doing this, we have made the route go from R1 to R2, and the same route has actually come down to R3 as well, right? We kind of got around the split horizon concept. And you can also see that because the next stop is R1, right, which is 10.1.1, it will now use the routing table, right? Show IP route, if you see, to reach 10.1.1, it has the route here, which it has learned through eIGRP, right? And it will use this 192.1.13.1, which is your direct path here between these both. So it clearly goes in line with what we learned earlier, right? BGP kind of helps you to distinguish or differentiate your control traffic from data traffic. The control traffic is going to route reflector to R2 and then to R3. whereas the data traffic, directly takes this path, right? So there is no bottleneck on your route reflector, right? Make sense? Yeah. So that's basically what we wanted to study here. Let's move on and do something very simple now, authentication, right? So let's say between R2 and R5 we want to do some authentication with the BGP. So BGP by default supports the MD5 authentication, right? So let's go to R2. I'll show you how we can do the authentication here. Let's wrap that as well, right? So we go to router BGP 1000, right? We do neighbor, and we already have set up neighbor relationship between R1 and R2 and R5, which is, this is how you do it. But now we put a password, right? Password, let's say we call it as Cisco. That's it. And on the other side, which is R5, so now the neighborship will go down here because only on one side you have the password, right? But now when we do it on the other side as well, which is here, router BGP 1000, sorry, not 1000, it's 500. On R5 it is 500, right? Yep. So neighbor 192.1.25.2, password would be Cisco. Make sense? Okay. Yeah, that's it. That's how you do the authentication. So by default it will obviously do MD5 hashing of the password, and that's so now if you see, you should still have the to show, right? You can see R2 has neighborship with 10.1. It should also have, let me do brief here, or probably show iBGP also should help. Yeah, so you can see the neighborship is there, and it is also learning the route from R5. Topic I want to talk about here is filtering, right? So filtering is very interesting. So filtering basically helps you to kind of prevent certain routes going into some other router, right? If you don't want, let's say on R1 and R2, between R1 and R2, you don't want say the 1.0 network which is there here, loopback network, you don't want it to be advertised to R2. Only that particular route you don't want to be advertised. So how do we accomplish this? Probably we go to R1. We will first, let me show you it. You will have the show iBGP, right? Yeah. So you see you have the one network here, but you don't want this one network, right, on R2. So what we can do is go and create the access list. You can do using access list or prefix list, right? I'll show access list because we have done prefix list before, and I've done with the access list as well on the other protocol, so you can anytime refer that. I'm just going to do it only here with access list. There you go. So this is access list. Obviously you have to permit the rest of the routes, otherwise by default it's a deny statement, right? So there you go, access list is done. Now you go to router BGP 1000 and we say neighbor, which is the neighbor 10.2.2.2, right? And we are saying distribute list. Use the distribute list command, name of the command is 1, and going out, right? So we have applied for the route which is going out, right, from R1 to R2. So on my R2 now, if I do clear IP BGP all soft, right, you can see now there is no more one network coming here, right? We have kind of filtered it and removed the one network from appearing on my R2, right? So that was how you can do filtering. You can also do the same thing and kind of get slightly different kind of advantages if you're doing using prefix list. Prefix list will give you the ability of filtering by looking at the network and the subnet mask, whereas access list just gives you control of the network portion, right? But you can try that out because I've done that in the previous other protocols as well. Okay, thanks.